Hello there, Mr. Sutton here, bringing you the AB Calculus 414 Extra Practice Number 1 solutions on basic related rates problems. For this problem, we have a point moving along the curve y equals x squared, so that we're given the rate of change of x with respect to time, and we want to find dy over dt when x equals 3. So this is definitely a related rates problem. We've got one rate of change, and we're trying to find another one. So we're going to set this up by implicitly differentiating everything with respect to time. So y, the derivative of that's going to be dy over dt. So this is our starting equation. We've got dy over dt equals, and now derivative of x with respect to time, we're going to have 2x times dx over dt. And at this point, we're going to plug some things in. So we're solving for dy over dt. So we're going to leave this unchanged. But x, they told us that that's going to be 3. And then dx over dt, they spelled it out. They said that was 2. So multiplying all that together, 2 times 3 times 2, that's going to give us 12. And in terms of the units, we have the rate of change. It is like a centimeters per minute sort of unit here, at least for dx over dt. And for x, they didn't really give units for that. So we're going to call this 12 centimeters per minute then. On this one, we have water falling on a surface, wetting a circular area that's expanding at a rate of 8 millimeters squared per second. We want to know how fast the radius of that area is expanding when the radius is 188 millimeters. So we have one rate of change. This area has a rate of change, and we want the rate of change of the radius. So this is going to be a related rates problem. We're going to start by writing an equation that ties all these things together, and then differentiate implicitly and find the missing value. So equation that ties it all together, we're talking about a circular area. So how about the circle area formula? A equals pi r squared. So taking the derivative with respect to time on all of these implicitly, derivative of a, that's going to be dA over dt. And pi r squared, that's going to be, using the power rule here, 2 pi r times dr over dt, everything differentiated with respect to time. Now we plug some things in. So what were we looking for? First off, they said how fast is the radius of the wetted area expanding. So we're looking for dr over dt. That means we need to find things for dA over dt and r. Well, dA over dt, that's how fast the area is expanding. And they gave us that. They said the area is expanding at a rate of 8 millimeters squared per second. So that's going to be 8 right there. And then for the radius, they told us the radius is 188 millimeters, or at least that's what it is at this exact moment in time that the problem's happening at. So we're going to write 2 pi times 188 times dr over dt. And at this point, we're just going to go ahead and divide both sides by 2 pi times 188 to get dr over dt by itself. So to do this on the calculator, just to make sure I don't lose anything, I'm going to use my fancy fraction form here. And we've got 8 over 2 pi times 188. All that comes out to, if I round it off to 3 decimals, about 0.007. So what should my units be on this? Well, we're talking about the radius, so that's going to be millimeters per second here. It's a single dimension unit. So there we are. For this problem, we have air being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. We want the rate of change of the radius of that balloon when the radius is 2 feet. And note that the volume of a balloon, or any sphere really, is 4/3 pi r cubed. So we're basically given one rate of change here, the rate of change of volume. We want the rate of change of the radius. So this is a related rates setup. We're going to come up with an equation, differentiate it implicitly with respect to time, and then solve for whatever's missing. So they already gave us the formula. We have the volume formula for a sphere here. This ties everything together. They gave us the rate of change of volume. Well, here's volume. They wanted the rate of change of the radius. Well, here's the radius. It's all in this formula. So writing that out, we're going to go ahead and take the derivative of this thing with respect to time. So each of these variables is an implicit function of time. Derivative of volume is going to be dV over dt. And over here, we're going to use the power rule. So 3 times 4/3, that comes out to 4 pi r squared times dr over dt. The radius is also a function of time. All right, so we're solving eventually for dr over dt. They wanted the rate of change of the radius. And just thinking ahead a little bit, that's going to be in units of feet per minute, because that feet is the distance unit here, and minutes the time unit. And this is a one-dimensional measurement. So now we have to find something to plug in for dv over dt and r. dv over dt, that's the rate of change of the volume. That's basically how fast your air is being pumped in. The balloon is expanding at a rate of 4.5 cubic feet per minute, so 4.5 is our dv over dt. And then for r, well, they want to know the rate of change of the radius when the radius is 2 feet. So this is the instant value of the radius is 2. So I'm going to write equals 4 pi 2 squared dr over dt. And now to get dr over dt, I'm going to go ahead and divide here. And I can simplify this stuff on the right to, this will be 16 pi. So basically I want 4.5 over 16 pi, or whatever that comes out to on the calculator. Let me figure that out. Since I have more than one thing being multiplied together in this denominator, I'm going to put it in my fancy fraction so I don't have to worry about parentheses. And that's going to come out to 0.090. And again, that's going to be in feet per minute. On this one, we have the edge of a cube expanding at a rate of 3 centimeters per second. We want to know how fast the volume is changing when each edge is 10 centimeters. So we've got related rates in here. We've got a rate of the edge of a cube, and also we have the rate at which the volume of the cube is changing. So we're going to get an equation that ties all of this together, and then we're going to use implicit differentiation with respect to time to get to the bottom of this question. So, equation that ties everything together. Well, how about the volume of a cube? That would help here. So we have v equals s cubed, and then if we take the derivative of this whole thing with respect to time, derivative of dv of v is going to be dv over dt, and derivative of s cubed, that's going to be 3s squared times ds over dt. So everything here is treated as a function of time. So ultimately, we want to know how fast the volume is changing. So we're trying to solve for dv over dt. And that means we better know what s and ds over dt are. Well, s, that is the edge, the length of the edge at this point in time that we're talking about. So that's this 10 centimeters here. And then ds over dt, that's how fast the edge is changing. So they said the edge was expanding at a rate of 3 centimeters per second. So that would be a positive 3 for ds over dt. And now we just have to multiply this together to get dv over dt. So this is 3 times 100, which is 300, times another 3 gives us 900. And the units on this, I mean, you can look at the rate of change here, dv over dt. Well, volume is going to be in cubic centimeters. Time is in seconds. So this is going to be cubic centimeters per second for that 900. On this one, we're given the equation z equals x squared plus y squared, and we want to find dz over dt given all this other information. So what we're going to do here, since we have multiple rates of change involved, we're going to set it up like a related rates kind of problem, where we basically differentiate everything with respect to time. So the derivative of z, that's going to be dz over dt. That's actually what we're looking for. And now derivative of x squared, that's going to be 2x dx over dt, so we're treating everything as a function of time. And then for y squared, that's going to be 2y times dy over dt. At this point, we just have to plug in everything, and hopefully we have enough to solve for dz over dt. So for x, well, they gave us that. That was 3. dx over dt is going to be 3 as well. And then we have plus 2 times the y value, 4. And dy over dt, they said, was negative 2. So just simplifying this, we've got, let's see here, this is 6 times 3, that's 18 minus 16 comes out to 2. For this problem, we have a balloon being deflated, so the radius decreases at a constant rate of 15 centimeters per minute. We want to know what rate air has to be removed when our radius is 9 centimeters. So if we're talking about the rate of removal of the air, basically removing space from this balloon, we're talking about volume. And we have a radius involved as well. We have multiple rates of change, a rate of change of volume, a rate of change of the radius. So we're going to set this up as a related rates problem. and we're going to differentiate everything with respect to time. We just need an equation that ties it all together. Oh wait, how about this volume equation over here? Yeah, this would do the job. So we have the volume of a sphere, because it's a spherical balloon, and we're going to take the derivative of everything now implicitly with respect to time. So we're going to treat everything as a function of time. So volume, derivative of that is going to be dv over dt. Everything gets its own little dt here. And then using the power rule on the right side, we got 3 times 4/3. That's going to be 4 times pi times r squared times dr over dt. So everything again gets its own derivative with respect to time. And now we have to find which quantity. Well, we want to know how fast air has to be removed. So that's talking about a change in the volume. We're solving for dv over dt. Well, that means we better have the radius at this specific point in time and also the rate of change of the radius. For the radius, they gave us that. That was 9. And then for dr over dt, this is the rate at which the radius is changing. Since the radius is decreasing at a rate of 15 centimeters per minute, we're going to call this negative 15. And then we should hopefully get a negative quantity as well for dv over dt because air is being removed there. So multiplying this all together, I'm actually just going to do this on the calculator. So multiplying all of that out, we end up with about negative 15,268.140. And since this is the rate at which the volume is changing, that's going to be in cubic centimeters per, let's see, what's our time unit here, per minute. On this one, we have a cylindrical tank, radius of 6 meters, filling with fluid at a rate of 108 pi cubic meters per second. We want to know how fast the height is increasing. And here's the volume formula for a cylinder. So we've got multiple rates going on here. We have a rate at which the volume is changing. That's this cubic meters per second rate. And we're asking about how fast the height is increasing. That's another rate of change. So this is a related rates problem. We're going to take a formula that ties all of this together. And this volume formula is pretty good because it's got volume and it's got height in it. And we're basically going to differentiate with respect to time and figure out the missing values. So there is one thing. I mean, they gave me this formula already, but there is something that I can throw in to help me out. They said that this tank has a radius of 6 meters. That isn't just at this specific point in time that they're talking about. This is like for all of time. This is the radius of our tank. So rather than writing out this formula the way it is, I'm actually going to substitute 6 for my radius. Because we know what the radius is, it's always the same thing. So I'm going to write this as volume equals pi times 6 squared height, or 36 pi height. And we'll go from there. All right, so taking the derivative now of everything with respect to time, derivative of volume, that's going to be dv over dt. And now we're just taking the derivative of 36 pi h, which is way better than having to mess with this r value here. So this is going to just be 36 pi times the derivative of height, so dh over dt. We wanted to know how fast the height is increasing, so we're solving for dh over dt. And that means we hopefully know what the volume's change is. Well, they said we're filling with fluid at a rate of 108 pi cubic meters per second. So 108 pi is going to be our dv over dt. And now to get dh over dt, I just have to divide both sides by 36 pi, which actually, as it happens, comes out neatly to 3. Now, what's the units going to be? Well, we have height over time for this rate of change. Height is measured in meters. Time in this one's measured in seconds, so that's going to be meters per second, 3 meters per second. On this one, we have a metal cube dissolving in acid such that the edge is decreasing by 0.58 millimeters per minute. We want to know how fast the volume is changing when the edge is at 7.5 millimeters. So we're talking about a rate of change of volume. We already have a rate of change of the edge of the cube. This is a related rates problem since there are multiple related rates here. And we need a formula that ties it all together that we can differentiate to get at those rates of change. So how about the volume formula for a cube? V equals s cubed. Taking the derivative of this, we're going to do this implicitly now with respect to time for everything. We're going to have dv over dt for derivative of volume. And derivative of s cubed is going to be 3s squared times, because we're using the chain rule here, times ds over dt, because s, like everything else in this problem, is an implicit function of time. All right, so we're ultimately trying to solve for dv over dt, because they said how fast is the volume changing. So that means we need to know what s is and also ds over dt. Well, s is the edge of the cube, the length of that at this specific point in time, and that appears to be about 7.5, they told us. So we'll plug that in for s, and for ds over dt, that's the rate of change of that edge. They said that the edge was decreasing by 0.58 millimeters per minute. Well, if you're decreasing by 0.58, then we should probably put negative 0.58 in there. And now I'll just multiply all this out on the calculator. So here we are. Numerically, this is all going to come out to negative 97.875. What's the units going to be? Well, the rate of change we're finding is dv over dt. This is volume over time. Volume has units of millimeters cubed in this one, and time has units of, it looks like, minutes. So this should be negative 97.875 millimeters cubed per minute.